The purpose of this lab is to demonstrate Faraday's law through the physical and computational simulation of a bar magnet falling through a conductive tube. In this lab, we'll use Faraday's law to determine the current of the foil tube. We'll use Lenz's law to determine the direction of the induced current. We'll use Newton's third law to determine the force exerted on the falling magnet. And we'll use Newton's second law to model the motion of the magnet via position and velocity. Experiment, the falling time was 1.87 seconds, and in the computational model, the falling time was 1.117 seconds. Here's a quick clip of me dropping the magnet north side facing down. Following this video, I could backtrack and determine the experimental falling time. We dropped our magnet north side facing down. This will induce a magnetic field, and the magnetic force opposing the gravitational force, leading it to fall slower. Here I have the experimental time and the computational time, and I also calculated the free fall time to show how they were all different from each other. On the right, I've drawn a free body diagram depicting the experiment. When determining why the experimental time and the computed time are so different to each other, you have to take into account the experimental things that could come into play. Some things that could lengthen the time would the angle it was dropped at, which could in turn affect the flux and the inductance and the friction from the inside of the tube. In our code, we will start with the physical attributes such as the mass and dimensions, as well as the initializing of various constants. We also create our foil rule and rings to make our calculations simpler. Here we calculate the magnetic field due to the bar magnet. Next, we calculate the derivative of the flux on each ring due to the falling magnet. Our while loop is a computational representation of the integral we'd use to calculate our magnetic field. Distribution of the tube by breaking it down into individual rings. Here we'll also have the calculations that allow us to calculate time. Near the bottom here, we have our code used to calculate the current, which we take the magnitude of our d flux dt, which would in turn be the EMF, and we divide it by resistance in order to obtain current. Here we calculate the magnetic force on each of these rings due to the falling magnet. We can then find the total force on the magnet via this net force equation on line 189. Now, using Newton's second law and kinematic equations, we can determine position and velocity. As exhibited on the graph, we can see that while the magnet is inside the tube, the velocity is constant and remains there for a total of 1.117 seconds. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? We know by Ohm's law that current equals voltage over resistance, and because resistance is getting smaller and smaller, then the current is getting bigger and bigger because the voltage is getting larger and larger, and those are directly proportional, we can tell by the equation. Large current means large magnetic field, which will in turn oppose the gravitational field, so that means that magnetic force will oppose the gravitational force in the magnet, creating a floating type phenomenon, which will decrease the rate of the falling magnet. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? Well, the rings with holes or slots in them would not contribute to the magnetic field because they would be considered an open circuit. And because there is less magnetic field opposing the gravitational field, in turn there is less magnetic force opposing the gravitational force. So this means that the falling rate of the magnet would increase and it would fall faster. In conclusion, we fulfilled our lab's purpose, which was to exhibit Faraday's law, or to observe and demonstrate it through the simulation of a falling magnet via an experimental experiment that happened physically and a computational simulation. We use numerous physics concepts to help in this exhibition of Faraday's law. We use Lenz's law, Newton's third law, and Newton's second law to help. When speaking about what surpassed in our experiment, we talked about how we dropped our magnet north side down and how this induced a magnetic field, which in turn induced a magnetic force, which would impose the gravitational force and would make the magnet fall at a constant velocity. Also talked about how in our computer code we started with creating objects, initializing values like the mass of a magnet or various dimensions like how the length of certain things, and in turn creating functions that would calculate the magnetic field due to the magnet falling through wings, and how the rings represent like an integral, how we add various things up, like how in integrals you slice things up. Near the end of the code, we saw how we could use kinematic equations as well as Newton's laws to calculate our force and motion. Then we showed the graph we obtained from actually running our computational code, and we could see how in the tube there was a constant velocity, but outside the tube there wasn't. And lastly, we went over hypotheticals like if the resistivity was reduced, and we know that resistivity is directly proportional to resistance, so we were able to see that. In turn, the falling rate of the magnet would decrease, and when we cut slits into the tube hypothetically, the falling rate would increase, making this a very effective and successful lab.